Finding an atomic radius from an FCC or BCC lattice constant. So FCC stands for face-centered cubic, BCC stands for body-centered cubic. So two different types of close packing of spheres in a solid state structure. So if I just draw a cube, attempt to make it look three-dimensional. Let's see, this question is asking us about FCC packing, so that's face-centered cubic. So what that means is we have an atom on each corner position and then at the center of each face. So ordinarily when you draw these, you may not draw the balls representing your atoms as being particularly large, just in terms of it's kind of easier to visualize. So I'm going to try and make these pretty large, and I'm going to start with the front face. Now, this may not be exactly perfect. Hang on, let's try that again. You know what? I'm going to do the one in the center of the face first so I can kind of eyeball this a little bit better. So we're going to pretend that these atom spheres are all the same size. Drawing on a computer is not so easy. So obviously the ones on the corner are going to slightly overlap each corner. I'm doing the best I can, okay? So pretend these are the same size and they're touching. That's good enough for me. Okay, so obviously the atomic radius is half of the diameter. So let's see if we can mark that on there with a different color. What's going to show up? Let's do black. Okay, so approximately that is one atomic radius, and so is that. And then we have two radii here, right? So hopefully we can all count out across the face that we have a total of 4 atomic radii, okay? So if I was to label this, this would be 4 times my radius, which will give the letter R, right? 4R going across. The trouble is, if we were trying to look at the edge length and trying to make a comparison there, that if we are close packed, let's see, I'll just draw one on here. Oh, that's black. I didn't mean it to be black, but here we go. So we're close packed, blah, blah, blah. Make that touch. Please make it touch. Okay, that'll do. So hopefully we can all agree on, even with my slightly crummy drawing, that we have a gap here, right? Mind the gap. So we need to find a way to link our edge length here of our unit cell, which we're going to just give the symbol L or A, whatever you like, to our unit, our number of radii. So if it's a cubic unit cell, each of these edge lengths are going to be L, right? So what we're actually going to do is we're going to take Pythagoras theorem, yay, Pythagoras, and we are going to look at the triangle that is bounded across the front edge of this unit cell, including those 3 atoms that are touching across the face. So Pythagoras theorem is the hypotenuse squared, that is squared, okay, equals, you know, the square of each of the 2 edges, forming that right-angled triangle. So hopefully we can all agree that here is a right-angled triangle, okay? So in terms of our face-centered cubic unit cell, our hypotenuse squared, the length in terms of the radius is 4r, and that'll be squared. And then our edge length is the same, okay? So it's going to be L. So we've got L squared, yeah, where's my little thingy? Plus L squared. So obviously you might have this on a formula sheet that you've memorized, but I might as well show you the derivation. So then we can tidy that up a little bit. Okay, so we've got 4R, and that will be squared equals L squared plus L squared is going to be 2L squared, like so. So seeing as both sides are squared, we can take the square root of both sides. So we can end up with 4R on the left equals 2L is then going to be root 2L. And what's a good way of writing root 2 on here? I'm going to have to come back and do it in a minute. So root 2L on this side. So I'm going to do a kind of approximate drawing of root 2L. So excuse me a second. I could have written 2 to the power of a half, I suppose. So there we go. 4R equals root 2L. So then we can just rearrange, right? So L is going to be 4R over root 2. L equals 4R over root 2, and I'll try and draw that and make that as pretty as I can, if you give me 1 second. So we have got a relationship between the edge length of the unit cell, L in this formula, and R, the atomic radius. So whatever units you put in for your atomic radius are going to be what you get out for the edge length. And don't forget, for a cubic unit cell, we might call that edge length L A, which is the cubic lattice parameter. Those are the same things, okay? So don't get confused if some people say L, some people say A. It's the same thing. Just means if you've got a cubic unit cell that edge length L is the same in the X, Y, and Z directions. So we've been given the lattice constant and we have to rearrange to solve for the radius. So what we're going to do is we're going to take that relationship that we've just derived and just rearrange and solve for R. So if I multiply both sides by root 2, I get L times root 2 equals 4R. I'm going to have to draw that root 2 in again. Oh, there's got to be a better way of doing this, but you know. Writing things sometimes is easier than computering things. So then I want to get R by itself, so I'm just going to divide through by 4. So my final relationship is going to be R equals L. That's a 1, not an L. Root 2 times L over 4. And I think I should actually be able to simplify that even more. This would be fine. That's going to work absolutely fine. But you can actually further simplify because, let's see right here, what have I done? R equals root 2 over 4. Was I trying to get it in terms of L? I was 4 over root 2. So R is going to be L times root 2 over 4, which is going to simplify. That is going to simplify to just 2 root 2, I believe. So I can actually go ahead and say R equals L over 2 root 2, which then I'm going to try and make that look a little bit neater. So either one is fine. Honestly, they're both going to work. It's the same number. It's like 2.8 something, right? So then I can just plug and chug. So I want to know what my R is going to be. R is L, which was 472 picometers. Divide that by 2 times the root of 2, which is just going to be a number. So 2 times root 2. Stick that in on my calculator and let's see what we get. Bam, bam, bam. The suspense. Such suspense. So 472 divided by 2 times, of course, you've got to work out how to make your computer happy with this, your calculator even. I think I have to use parentheses there. I get 166.8772, blah, 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 picometers. So I think I should be doing this to 3 sig figs, given that my value for the lattice constant was given to 3 sig figs. So I'm going to say 167 picometers to 3 sig figs. Okay, so I'm going to do a little bit of rinse and repeat and see if I can find another one that's body-centered cubic. Come on, give me body-centered. Give me body-centered. Body-centered. Okay, so if you haven't already written those equations down, worked out how to drive them, we're going to do the same thing with body-centered now. And of course, for body-centered, there's just one atom at the body center site and all the others on the corner. So we don't have touching across a face like we do in the face center cubic. So we've got to look along that body line. So let me do a quick cube for body center cubic, trying to make it look like a cube as much as I can. But you know, little limited to what I can do here, but hopefully you get the idea. So we're going to go across the diagonal, going straight through the body to get those touching atoms. So let's get a sphere. Let's pick a color, any color. So one in the body. So this is right in the body center. And then we got 8 atoms on corners. Maybe I should have done that with the sort of see-through thing so we could see a little bit. Let's try see-through. Let's be fancy, right? So this is right at the body center, see-through, right? So this is going to be on the back right corner, as you can see from your screen. So back right corner and then front left corner. Hopefully I can make you big enough. No, not happy with that. Okay, Sort of like that. So they just pretend they're touching, right? So the diagonal that we are talking about is going from this back right corner here to the front left corner. And that is going to be our right angle triangle that we're going to Pythagoras again. Okay, so this is going to be the edge that has our 4R along it. So hopefully we can see those 4 radii. Let's change color. So 1 atomic radius, kind of sort of, sorry for my crummy drawing, 2, 3, 4, like that. So that is going to be our 4R along this edge length right here. Okay, so this is obviously going to relate to our edge length L. Okay, but this, well, we can't just get this right off the rip. So we're actually going to have to do 2 Pythagoras's here. Okay, so let's pick a different color here. Green. Okay, so we're going to do this triangle first. Okay, so this one does have L and L as the edge lengths, right? L and L. So we're going to be solving for the hypotenuse to help us with our red triangle. Okay, so let's do that first. So our hypotenuse squared equals each of those edge lengths. So that's going to be L squared plus L squared in this case. So we can simplify that to my hypotenuse squared is 2L squared. So now this edge length here is 2L squared. So now I have everything I need in order to be able to do this red triangle right here. So 4R is going to be the hypotenuse, right? So 4R all squared. And then that bottom edge length is just going to be L. So just substituting to Pythagoras, that'll be L squared. And then plus that other edge length we know is 2L squared. So we have 2L squared. I should have written that that is actually the root of 2L squared as I've labeled on there. I solved for 2L squared, right? A bit lazy there. Okay, so now this is what we have to fix, rearrange, so we get a relationship between R and L. Before we go on, I'm actually going to fix that right there, just so we know that that would have to be the root of 2L squared. I could have just drawn a root. What is wrong with me? But we don't need to actually solve for that because we're squaring it again to put it into Pythagoras, right? Right, let me just draw a little. Oh, it's green. How nice. Okay, so anyway, back to where we were. So hopefully we can see that we can tidy this up a bit. So 4R all squared equals L squared plus 2L squared gives me a total 3L squared. Okay, so then we should be able to simplify that by just taking the root of both sides. So we are going to end up with just 4R on the left. I like that already. We are going to have to do root of 3, but then the root of L squared is just going to be L. So I'm going to have to draw in a little root 3 here. Let's make it not green because that's going to jar. Okay, root 3L. So now we have a relationship between 4R and L. So if we get that, so L is the subject, we're just going to divide through by root 3. So L equals 4R over root 3. Let's just make that look a little bit prettier. So that is our relationship that we've derived just from using good old Pythagoras. I wonder what Pythagoras would have thought about face-centered cubic and body-centered cubic crystal structures. I'm sure he would have been delighted. Okay, so there is our relationship between L and R. Okay, for this question, we're being asked to solve for R, so we're going to have to rearrange. So I am just going to go ahead and multiply both sides by root 3. So we're going to have root 3 times L equals 4R. I guess I'm going to have to draw that root there before I forget it's there. So root 3 is just a number times L equals 4R. So then I can divide both sides by 4 to get R on its onesies. So then we have R equals L root 3 divided by 4. And that is good enough for me. So then it's just a plug and chug. So L times root 3, don't forget the root, or 3 to the power of half. Take the time to make sure your calculator is happy with however you put that in. So I guess without any further ado, now I've shown you whether we can have the equation in terms of L or R. In this case, we have been given R and we are asked to find L. So I'm actually going to use the top version where we're solving for L this time. So L is equal to 4 times R. So 4 times the radius is 4 times 144. That's just going to give us our answer in picometers divided by root of 3. So let me just tidy that up a little bit. So root 3. So let's stick it in the calculator. Again, you may need to put parentheses around the root 3, etc. to make your calculator happy with you. So I get L equals 4 times 144 divided by root 3. I have to put the 3 first and the root all in parentheses for it to work. And that comes out as 332.5537 blah, 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 picometers. So to do this to, I would say for the question 3 sig figs, I'm going to say L equals 333 picometers, right? Because 0.5 means we're going to round up. All right, so hopefully that's helpful for you. You see the relation for face center cubic and body center cubic unit cells between L and R, and importantly, you know how to derive them. So if you aren't taking an exam where you get a formula sheet or something, Pythagoras has got your back.